Welcome to True Projects. In this video, we are going to explain about detection of plant leaf disease using deep learning approach. Introduction. The project's introduction emphasizes the need of early diagnosis of plant disease for efficient agricultural yield. It adds that typical illness detection systems entail manual identification by human experts, which can be time-consuming and expensive. The project discusses the use of computer vision and artificial intelligence to detect plant disease automatically from raw photos. The introduction also defines deep learning, which is a sophisticated approach of machine learning that uses neural networks to automatically extract characteristics from visual patterns. The project focuses on using deep learning, primarily convolutional neural networks, CNN, to detect plant leaves and recognize disease. Objective. The project's goal is to use deep learning techniques to create an effective solution for identifying different illness in various plant kinds. The project's goal is to train deep learning models to identify and recognize plant disease and their absence by employing a camera to gather images as a basic for recognizing various forms of plant disease. The technology is intended to detect and recognize a variety of plant varieties including apple, corn, grapes, potato, sugarcane and tomato. Requirements. The requirements of the project are hardware requirements and software requirements. In hardware requirements, we have operating system Windows only, processor i5 and above, RAM 4GB and above, hard disk 20GB and above. In software requirements, we have Python IDEL with 3.7 version. Methodology. To implement this project, we have designed the following modules. The first module is upload plant disease dataset. In this step, we need to gather a dataset of plant leaf images where each image is labeled with the corresponding disease or healthy status. The dataset should be properly organized and split into training, validation and testing sets. Second module is pre-processed dataset. Data pre-processing is essential to ensure that the dataset is ready for training. Common pre-processing steps include resizing images to a fixed size, normalizing pixel values, data augmentation, that is rotating, flipping and zooming images, and creating batches of data for efficient training. Third module is run VGG16 algorithm. VGG16 is a deep convolutional neural network architecture with 16 layers, primarily used for image classification tasks. In this step, we use the VGG16 model and fine-tune it on your plant disease dataset to perform disease classification. Fourth module is run ResNet50 algorithm. ResNet50 is another popular deep neural network architecture known for its skip connections and residual blocks. We will use the ResNet50 model and fine-tune it on your dataset to perform disease classification. Fifth module is run ResNet30 algorithm. It's possible that ResNet30 might refer to custom modification of the ResNet architecture with 30 layers. Similar to the previous step, we will use this custom ResNet30 model and fine-tune it on your dataset for disease classification. Sixth module is run Inception V3 algorithm. Inception V3 is a deep learning architecture that uses inception models with multiple filter sizes to capture different feature scales. We will use the Inception V3 model and fine-tune it on your dataset for disease classification. Seventh module is run AlexNet algorithm. AlexNet is one of the pioneering deep learning models famous for winning the ImageNet competition in 2012. It's an early CNN model with several convolutional and fully connected layers. We will use AlexNet and fine-tune it on your dataset for disease classification. Eighth module is run custom CNN algorithm. A custom CNN algorithm refers to a custom designed convolutional neural network architecture tailored specifically for the plant disease classification task. We will design this architecture and train it from scratch on your dataset. Ninth module is genetic algorithm feature selection. Feature selection is crucial to improve the model's performance and reduce computation time. Genetic algorithms can be used to optimize feature selection by evaluating different feature combinations and selecting the most informative features for the disease classification task. 10th module is comparison graph. After training all different models, VGG16, ResNet50, ResNet30, Inception V3, AlexNet and custom CNN, we will evaluate their performance on the test data. The comparison graph represents a visual comparison of the accuracy or other performance metrics achieved by each model, allowing to access in which one performs the best. 11th module is detect disease from test image. Once you have the selected best performing model, we will use it to detect disease from unseen test images. The model will take an input image of a plant leaf and predict whether it is healthy or affected by a specific disease. Execution. For the execution of the project, we need to open the code folder. This is the code folder. This is the dataset folder. In the dataset folder, we have different files which we will use during the execution of the project, in which we have the all images of the leaves. And this is the model folder. This folder contains pickle and .h files stored, which contains algorithm information. These pickle and .h files can be loaded into the project code during runtime to utilize the trained models. And this is test images folder, in which we have the test images which we have used during the execution of the project. This is main code file. This is run.batch file. Instead of executing our project in the command line interface, we have created Windows batch file to execute the project. Double click on run.batch file. A graphical user interface will pop up. This is the graphical user interface which we have created using Tkinter library in Python. Using this GUI, we will interact with the project. Click on Upload Plant Disease Dataset to upload the dataset. Select Dataset and open it. So we can see that the dataset is loaded. Now click on Pre-process Dataset to upload. So after pre-processing the dataset, all the images will be processed, and this is one sample test image. So here we can see that after pre-processing, we will get the total dataset processed image size. Now click on Run VGG16 algorithm to train the algorithm and get its accuracy. After training VGG16 algorithm, we will get its precision, recall, F1 score and accuracy. And this is the VGG16 algorithms training accuracy and loss graph. So here we can see that the x-axis represents iterations or epoch and y-axis represents accuracy or loss. And the blue color line represents VGG16 algorithm loss, and the green color line represents VGG16 algorithm accuracy. Now we will close the graph. Now click on Run Resident 50 algorithm to get its accuracy. So after training Resident 50 algorithm, we will get its accuracy, precision and recall, and this is the training accuracy and loss graph of Resident 50. So here we can see that x-axis represents iterations or epoch and y-axis represents accuracy and loss, and the blue color line represents the accuracy, green color line represents the loss. Now we will close the graph. Now click on Run Resident 30 algorithm to get its accuracy. After training ResNet 30 algorithm, we will get its precision, recall, F1 score and accuracy. And this is the accuracy and loss graph of ResNet 30. So we can see that the x-axis represents iterations or epoch and y-axis represents accuracy and or loss. And the blue color line represents loss and green color line represents accuracy. So we can say that with each increasing epoch, accuracy increases and loss decreases. Close the graph. Now click on Run Inception V3 algorithm. After training Inception V3 algorithm, we will get its precision, recall, F1 score and accuracy. And this is the accuracy and loss graph of Inception V3 algorithm. So we can see that x-axis represents iterations or epoch, y-axis represents accuracy or loss, and the blue line represents loss and green line represents accuracy. Now close the graph, click on Run AlexNet algorithm to get its accuracy. After training AlexNet algorithm, we will get its precision, recall, F1 score and accuracy. and this is the accuracy and loss graph of AlexNet algorithm. X-axis represents iterations or epoch, y-axis represents accuracy or loss, and the blue line represents loss, and the green line represents accuracy. Now close the graph, click on Run Custom CNN Algorithm to get its accuracy. After training custom CNN algorithm, we will get its precision, recall, FN score, and accuracy. And this is the accuracy and loss graph of custom CNN algorithm. X-axis represents iterations or epoch, y-axis represents accuracy or loss, and the blue line represents loss and green line represents accuracy. Close the graph, click on genetic algorithm features selection to extract features from CNN and then train with genetic algorithm to select important features. So after training the genetic algorithm features, we will get the total features found in dataset before applying genetic algorithm and after applying genetic algorithm. Now click on comparison graph. So this is the comparison graph. On the x-axis we have the different algorithms, and on the y-axis we have the accuracy value. So here we can see that custom CNN is having the highest accuracy compared to the other algorithms. Close the graph. Click on detect disease from test image to upload test images and get the predicted output. So here I am selecting the 5th leaf, open it. So here we can see that on top of this image the plant disease predicted has apple scab. So this is an apple leaf and this leaf is having an apple scab. So this leaf is diseased. So now we will select another leaf. I'm selecting the first leaf, open it. So we can see that on top of the image plant disease predicted as grape leaf blight, Scrapios leaf spot. So this leaf is having some spots and there is a name to the spot. So this means that this grape leaf is infected. Now close the graph. In this way we can test all the images which are present in the test images and find whether that leaf is infected or not. And the final conclusion of the project is, the project concluded that the proposed deep learning model can help farmers detect and recognize plant illness. Using convolutional neural networks, the project was able to detect and recognize 32 different plant kinds and plant illness. The trained model can be used to detect and recognize plant illness in real-time photos. In the future, additional plant kinds and plant disease of various types may be added to the existing dataset to improve the trained models. Other CNN designs may utilize alternative learning rates and optimizers to experiment with the model's performance and accuracy.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.